This slidecast covers sequential containers. We have a lot of objectives in this chapter. We want to become familiar with the standard template library. We want to understand how to use the vector class, understand the difference between a shallow copy and deep copy. We'll study linked lists. This is kind of the first major data type or data structure we'll discuss this semester. We'll see single, double, and circular versions of this. We'll introduce structs. We'll understand what iterators are. You'll understand how to implement the STL list class. You'll learn how to implement the iterator for a linked list, how to declare aliases and use delegation, become familiar with the STL sequential containers, introduce functions in the algorithm header. Now, so far we've considered one data structure that we can use in our programming, and that's the array. C++ developers have provided more tools for programmers by providing a rich set of data structures written as C++ template classes. So these template classes are all part of the standard template library. And in this chapter, we're going to discuss the STL classes called sequences. A sequence has the property that elements can be inserted or removed anywhere in the sequence, not just the beginning or end. Some sequences are indexed, so you can access them in arbitrary order using a subscript to select an element, just like you're familiar with using an array that way. And for other sequences, you have to start at the beginning and process the elements in order. In this chapter, we'll discuss iterators and their role in facilitating sequential access and random access. We'll discuss vector and list classes, how they're the same and different. And we'll show how these classes implement a common interface requirements for sequential containers. Now let's talk about template classes and the vector. A template class is a class that stores and processes a collection of information. Here is the declaration of a template class. So we have the class named SomeContainer, and we have the keyword template, followed by an angle bracket type name, which is a keyword, and then t. Now this parameter t is a placeholder for the actual data type of the information to be stored in some container. So a template class tells us that we will have a container that contains a given type t, and then in our program, we'll declare instances of this SomeContainer class, and it's at that point that we will declare the type that's in a given container. So here's two lines that each line creates an instance of the class SomeContainer. This container call lengths is a container of ints, and people is a container of person instances. This is very useful because now I don't have to declare at the class level, I don't have to declare a class of ints and then a class of people and a class of other data types. Okay, so this is a kind of a useful way to eliminate a lot of redundancy that we might otherwise have to do if we didn't have template classes. The same operations can be formed on both instances. So at compile time, the actual data type is substituted for the parameter t to create the desired instantiation of SomeContainer. A vector template class is an improvement over an array. We talked about this in class the other day. So a vector is based on an array, so you can select the elements in arbitrary order using a subscript. And the vector supports the following operations that an array does not. You can increase or decrease its length. You can insert an element at some specified position without writing code to shift the other elements out of the way to make room. And you can remove an element without having to write code to shift the elements to fill the gap. The shifting on insert and remove takes place automatically for you. Now, vectors are most often used when a programmer wants to add new elements to the end of a list, but still needs the capability to access the elements stored in the list in arbitrary order. So we needed this in this telephone directory application from Chapter 1. we added new entries at the end, we needed to find numbers for entries already in the directory. The size of a vector automatically increases as new elements are added to it. The size decreases as elements are removed. Now, if an insertion is not at the end of the vector, existing entries are shifted automatically to make room. And if an element other than the last one is removed, then the other entries are shifted automatically to close up the space that was vacated. The number of elements in a vector currently contains is returned by the member function size. Each vector also has a capacity, which is the number of elements it can store. When the vector size is equal to the capacity, then the capacity is increased automatically. So a vector is a template class, so you can declare a vector of objects to hold objects of any type. Here's a declaration of my vector, which is a vector containing strings. Now, to allocate storage for a vector whose elements are string objects, here's a declaration in our program. Initially, my vector is empty, and these four statements add these four strings to the vector using pushback. The pushback method places the value at the end of the vector. So here's what the vector would look like after those four operations. Then if we have this my vector with these four strings and we call insert with the index 2 and doc, then this is going to insert doc at subscript 2, and it will automatically push jumpy and happy over one index to make room. So jumpy and happy, the indexes of 2 and 3 change to 3 and 4. We can use pushback to add a dopey to the end of the vector. If we're given this vector and we say erase 1, we'll go to subscript 1 and remove awful, and the others are automatically moved up one index. So our size decreases by 1. Given this vector, you can access elements using a subscript, just like an array. So my vector sub2, if we take that value and assign it to the string dwarf, then the string jumpy is going to be assigned to this variable dwarf. Doesn't make any change to my vector. We can replace elements. On the left-hand side, if we specify my vector sub2, then the string sneezy is assigned to that location. In this case, it'll replace jumpy. Vector class is part of the standard library, and it's in the header file vector. In the C++ standard library, there's a second template parameter called an allocator. Now, the library provides a default value that's adequate for most purposes, so you can look at Appendix A for some discussion about allocators. Here is a table that shows member functions of the vector class and a description of their behavior. We overload the subscript operator. This first one returns a reference to the element. It's const, so we can use this on the right-hand side of an assignment statement. Here we overload the operator, and we can use this on the left-hand side of a target assignment. Here we have the at method, which is a way to go to a particular index location and grab a value from the array. Here's the size method that returns a number of items stored in a vector. We can resize the vector, changes the size to new size. We can swap to exchange the contents of this vector with the contents of the other vector. So swap takes a parameter other of type vector. Pushback adds a copy of the value at the end of the vector. We've got insert and erase, which we've seen examples of before. Popback removes the last item from the vector. Notice a lot of these parameters are of type size_t. We talked about that in class. That's an unsigned int and is used whenever we expect non-negative numbers. Now, because item type is determined when the vector is created, the actual argument types and return types for these functions may be different in different instantiations. So notice all these occurrences of item type. So because it's a vector class, the class name was declared with the template parameter of item type, and that will be replaced at compilation time when we declare instances of vector with a specific type. So I mentioned size t being an unsigned int. The functions insert and erase are defined differently in the standard template library, but the form shown in the table is what we will implement in section 4.3. And at the end of the chapter, we'll revisit this idea and we'll modify our sample implementation to be like this standard one. There are 2 entries in the preceding table for the subscript operator and 2 for the member function at. And the first entry returns the value of the specified vector element. That's indicated because we have this const at the beginning and the end of these entries. And this value can't be changed. The second entry for each is a reference to an element of the vector, and its value can be changed. So here both of the following statements retrieve and display the value of element 2 of vector v, a vector of integers. So here we can use subscripting because we've overloaded the subscript operator, or we have a method called at, and they both perform the same operation of retrieving element 2. Here are 2 statements that both add 6 to the value of element 2 in our vector. Now in these statements, the reference to element 2 retrieves a value of vector v that is not changed. And in contrast, both references to element 3 change its value. So on the right-hand side, we'll use this const. The return type is const, meaning it can't be changed. Back up and remind you. So here's this, we're overloading the operator, and notice this const. This const refers to the reference of item type that's returned. So this can't be changed, so that thus we could use it on the right-hand side. But on the left-hand side, we use this definition of the operator because we need to be able to update it. And that concludes this slidecast.